Welcome to lecture number 11 on linear programming problems under this course on computational mathematics with SysMath. In this lecture, we are going to look at a very important concept called duality. To every linear programming problem, there is another problem which is also a linear programming problem, and that is called a dual linear programming problem. And the solution of the dual can be obtained from the solution of primal problem and vice versa. So once you solve either the primal problem or the corresponding dual problem, you can, in case it has a solution, you can find the solution of both. That is the thing that we will see. Now, solving a linear programming problem via dual sometimes may be easy, especially when you have less number of constraints than the number of variables. Then once you write the dual of a linear programming problem, and then you can solve that linear programming problem using simplex method or whatever is the appropriate method, that may be simpler than solving original linear programming problem. And that is why it is important sometimes to understand the dual rather than the primal problem, which is the original problem. Now let us look at how we are going to write dual of a linear programming problem. So for this purpose, we will consider our standard problem, a minimization type, which is minimize z is equal to c transpose x, subjected to the constraints x greater than equal to b and x not negative. So this is the problem we will consider, and we will write dual of this problem. So we will call this problem as primal problem, and we are going to write dual of this problem. And we know that any linear programming problem can be converted into this form, and therefore we can always write dual of any linear programming problem. Okay, so the dual of this linear programming problem, which is given in this P, is of the form maximize W is equal to B transpose Y, subjected to A transpose Y less than equal to C and Y non-negative. So if you notice the changes that happens in dual of primal is that there is a new variable, namely Y, and since suppose A is M cross N matrix, A transpose will be N cross M matrix. Therefore Y will have M variables. So Y is M variables, which is the number of constraints in the original problem, that is primal problem P. And if you look at the right hand side is C, which was a coefficient of the objective function, right? So that also indicates that the number of constraints will be same as number of variables in the objective function. And the number of variables in the primal is number of constraints in the number of variables in the dual is going to be number of constraints in the primal. Okay, right. So essentially what has happened is the role of B and C have changed. Okay, in the primal dual, the roles of B and C are reversed. That is what has happened. And the matrix A is now here A transpose in the dual. So this form of duality is known as symmetric form of duality, right? So what was the original primal problem? It was minimization type subject to Ax greater than equal to B, right? And in the dual of that has become maximization type of problem subject to A transpose Y less than equal to C. So greater than equal to has become less than equal to, B has become now C, and C has become B. And of course the design variables, the new design variables are also non-negative. So this is what is called dual of this primal problem B. Right. Now let us look at how to find dual of an arbitrary problem. So of course, as I said, in case you have any linear programming problem, it can be converted into this standard form, which is minimization type subject to Ax greater than equal to 0, X non-negative by appropriate transformation. So therefore, we can first we can convert this problem into a standard form, that is in as in P, and then we can write its dual D. So that we can always do it. However, if you look at the problem in the standard form, that we always looked at minimization problem subject to equality constraint with non-negative design variables. So how to write dual of this problem rather than converting this instead of converting this into a standard less than equal to sign, how do we write? So of course, as I said, first thing we need to do is we can convert this problem into standard problem and then write its dual. So how do we do that? So first is the problem is minimization, which was original the case, that we don't have to do anything with the objective function, but this equality can be converted into inequalities, because ax equal to b is same as ax less than equal to b and ax greater than equal to b. So first we can write ax greater than equal to b, and then the second constraint is ax less than equal to b. Now ax less than equal to b, we can multiply both sides by negative 1, and then it becomes minus ax greater than equal to b, greater than equal to minus b. Therefore now you have the problem which is minimize C transpose x subject to ax greater than equal to b and minus ax greater than equal to minus b. So you have got two set of constraints. Now these two set of constraints can be combined in one, and how do we do that? Let us write this a and minus a as a matrix, maybe block matrix a, and below it's minus a, and then here you have x which is greater than equal to b and minus b. So now instead of a you have a block matrix a and minus a. So that is new problem. So if you think of this whole thing as another matrix, let us say capital M, and this b minus b as let us say let us say b dash, then you have got mx greater than equal to b dash and x non-negative. Right. Now let us do another transformation. So this if you write now the dual of this linear programming problem, what will you get? You will be getting maximize b maximize. So one you will have to introduce one constraint, set of constraint with respect to the a x, another one with respect to minus ax. So let us say we will introduce u with respect to constraint a and v with respect to constraint minus a. So u will be u1 u2 um and v will be v1 v2 vm. So now this the constraint will become now a transpose minus a transpose uv, which is same as saying a transpose u minus a transpose v less than equal to c. And here the objective function will become now u transpose v transpose that is row wise times b and minus b. So that is same as saying u transpose b minus v transpose b, that is your objective function. So therefore that can be written as u minus v transpose b and subject to these constraints. Right. So that's the modified problem, that is the dual problem of the standard linear programming problem of equality type. Now let us do one more transformation. Let us write u minus v. Remember, u and v are non-negative. So if I look at u minus v as another variable, let us say y, then y will be unrestricted, because u and v are non-negative. So u minus v can take positive as well as negative value including zero value. Therefore u minus v can take any real value. Therefore this is unrestricted. So now the problem will become now fx, maximize fx is equal to y transpose b subject to a transpose y less than equal to c and y is unrestricted. This form of duality is called asymmetric form of duality, right? So you can not only write dual of the problem which we have considered in standard form, but also the problem which involves equality type, right? Except that when you have equality constraints, the variable, the dual variables will become unrestricted. Okay, now let us take an example. So this is an example. Let us ask it to show. This is the problem. which is to minimize 2x1 plus 3x2 plus 4x3 plus 5x4 subject to first constraint which is greater than equal to type, second constraint is also greater than equal to type, third constraint is equality type, and fourth constraint is less than equal to type. And you have x1 greater than equal to 0, x2 unrestricted, x2 can take in real value, x3 is greater than equal to 0, and x4 is less than equal to 0. So this problem involves all sorts of design variables, negative, non-negative, and then also unrestricted. And also the inequalities are greater than equal to, less than equal to, and equality. So again it involves all possible types of inequality. Objective function is of course minimization type, right? So if you find out dual of this, what you need to do, you need to convert this problem into the standard problem, which is minimization type and greater than equal to inequalities. So one can do that and write its dual and then do the transformation as we have done here. So wherever you have less than equal to design variables, you can take negative of that in order to make it positive. When you have unrestricted constraint, that you have to write difference of two non-negative variables. Okay. However, SAYS has an inbuilt function to find its dual. So let me make use of that and show you what is its dual. So let me say, so here we have considered the problem P. This is the problem, and then let us say P dot dual will give you the dual of P. Let us see what is the dual. Now let us compare this primal and this dual, and then see what are the changes that has occurred. Of course, the minimization objective function has become maximization in dual. Now here it involves 4 design variables, namely x1, x2, x3, x4. x1 is non-negative, x2 is unrestricted, x3 is greater than equal to 0, and x4 is non-positive, right? So with respect to 4 variables, with respect to 4 design variables here, each one you will get a design variables with respect to each constraint in the primal problem. You have a design variables, namely y1, y2, y3, y4. So here this if we call this coefficient matrix as A, this coefficient matrix will be A transpose. The design variables will be y1, y2, y3, and the right hand side here is 10, 6, 5, 15 and 8, which has become now coefficient of the objective function. So 10y1 plus 6y2 plus 15y3 plus 8y4 subject to these constraints. Now see what has happened. Second variable in the objective, in the primal, is unrestricted. So look at the second constraint in the primal, that is now equality, right? The first constraint is greater than equal to, so the constraint in the primal has become less than equal to. For example, the last constraint in the primal is less than equal to, so the last constraint in the dual is greater than equal to, right? So that these are the changes, and you look at the first variable y1 is greater than equal to, y2 is greater than equal to, y3 is unrestricted. Which one is unrestricted? Y3 corresponds to the third constraint in the primal, which is equality type. So when you have equality type constraints, the dual variable is corresponding to that will be unrestricted, and here y4 was less than equal to, therefore x4 was less than equal to, therefore in this case y4 becomes less than equal to. So here this fourth constraint was less than equal to, which is opposite of the standard one, so that particular constraint has become greater than that particular variable has become less than equal to. So these are the changes. Let me summarize these observations that we have done. Okay, so what are the observations here? So in the primal and dual, if you compare, if you look at the primal variables, ith primal, if you look at the primal problem, if I look at the ith constraint, if ith constraint is greater than equal to, the ith dual variable, that in this case we have written yi will be greater than equal to. That's exactly the case. So look at for example, the primal problem, which is the first constraint which is greater than equal to, and then look at the dual variable y1, this is greater than equal to. Similarly, in case the ith constraint is less than equal to, that is the case here in the fourth one, then the ith variable will be less than equal to, which is the y4 in this case. If the ith constraint is equality in the primal, then the ith variable will be unrestricted. That is the case here. The third constraint is equality. The third variable in the primal is unrestricted. Next, with respect to the jth variable in the primal, if jth variable is greater than equal to, then ith constraint will be less than equal to. That is what you can see here. So first design variable in primal is greater than equal to. So look at the first constraint, that is less than equal to. Next, if the jth variable is less than equal to type, if jth variable is less than equal to type in the primal, then the I should write here j, this would be j here, not I, j, this should be also j, this should also be j, right? So if jth variable in the primal is greater than equal to, jth constraint in the dual will be less than equal to. If jth variable in primal is less than equal to, then jth constraint in the dual will be greater than equal to, and in case jth variable in the primal is unrestricted, the jth constraint in the dual will be equality type. That is what we have observed in this problem, and not just we observed in this problem, but if you write dual of any linear programming problem, this is what will happen. So if you have understood this, you can write dual of any linear programming problem without even converting the linear programming problem into a standard form. If you just remember these observations, you can always write. Okay, fine. So let us look at, so we have constructed dual of the primal P. Now suppose we take dual of the dual, right? Any linear programming problem has its dual, and dual is a linear programming problem. Therefore, if I want to find dual of the dual and then see what you get, what can you expect? This is similar to if you have a matrix, if you take transpose and take transpose of it, you get the original matrix. That's exactly that's exactly what has happened, right? Dual of a linear programming problem will be the original problem, that is primal. If you compare this with the original problem, these two are exactly the same. So dual of dual is the original problem. Okay, now let us look at some results. We are not going to prove these results, but we will quote these results. For proof, you can look at some standard text on operation research. So the first problem, which we just now observed, dual of dual linear programming problem is the primal. That is the first result or observation. The next one is weak duality theorem. So what does it say? Let X be a feasible solution for a primal problem in the standard form. Okay, the standard form which we have considered is minimization type and greater than equal to inequalities, the constraints. And let Y be a feasible solution of the dual. So we have feasible solution for primal X and feasible solution for dual Y. Then if you look at the value of the objective function at X of the primal and value of the objective function at Y of the dual, there is a relation. This says that Z, which is C transpose X, is always bigger than equal to B transpose Y, which is equal to W. Therefore, if you take any two feasible solution X and Y of primal and dual respectively and compare the value of the objective function, then this is the relation. Z is always bigger than equal to W, right? So in particular, this weak duality theorem says that a feasible solution to either problem yields a bound on the optimal cost, right? So remember, when we write dual, in the primal you have cost variables and the design variables, right? And the role gets reversed. Therefore, this gives you a bound, right? Every feasible solution of primal and dual is related by this relation, so it provides you bound for either. Right, that's the first observation. And if so from this result you can infer that if the primal is unbounded, then the dual will be infeasible, and vice versa. If the dual is unbounded, then the primal is infeasible. That follows from this result itself. Okay, that is quite easy to prove. Next result says that in case you have found x naught, which is a feasible solution of the primal, and y naught, a feasible solution to the dual, such that the value of the objective function at x naught and y naught of the primal and dual, that is C transpose x naught and C transpose y naught, are equal, then this x naught and y naught are also optimal to the respective problem, right? And that also means that the value, if it is optimal, then the optimal value of the primal and dual are going to be the same. So that is what is this result says, right? So this actually provides you a kind of way in which you can approach to solve primal and dual problem. Next result is what is called strong duality theorem, and this says that if you consider a pair of primal and dual problems, that means consider primal P and its dual D, if one of the problem has an optimal solution, then so does the other, and the optimal objective function value are the same. So if you know that somehow, if you know that the one of the problem is optimal, then the other one will also be optimal, right? If primal has an optimal solution, then dual will also have an optimal solution, and vice versa. That is what is called strong duality theorem, right? Now let us look at another result, which is called complementary slackness condition. Actually, this provides you some kind of relationship between the values of the design variables of the primal and objective primal and the dual, right? And what does it say? So consider a pair of primal dual problem. The feasible solution x and y of the dual pair of problem. So x is a feasible solution of primal, y is a feasible solution of the dual, right? In any form, either it is symmetric form or asymmetric form, they are optimal if and only if following conditions are satisfied. The first condition is C transpose minus y transpose Ax is equal to 0, and second one is y transpose times Ax minus b is equal to 0. Now if you play with these two equations, if you write this in component form, what it means, just let us look at the first one. C we will write as C1 C2 Cn. So the first one is the C transpose, that is the row matrix C1 C2 Cn, minus this y transpose will be y1 y2 ym. We are assuming that we have m constraints and n design variables, times A we will write as column matrix A1 A2 An. So we have either C1 C2 Cn minus y1 y2 yn times A1 A2 An times x. This is equal to 0. Now if you look at the component wise, if you write this multiplication component wise, what it means is that Ci minus y transpose Ai times x is equal to 0. Now what is Ci minus y transpose Ai? This is nothing but the ith constraint of the dual problem, right? So it says that xi times the ith constraint, when you bring the right hand side to the left hand side, times xi is equal to 0. So if xi is positive, then this coefficient, that is Ci minus y transpose Ai must be 0. That simply says that if xi is positive, right, then the corresponding ith constraint in the dual will be equal to 0, will be satisfied. And conversely, if you now play with the second equation and then interpret this in terms of coordinate, it would mean that if yi is positive, then the ith primal constraint is going to be equality, right? So sometimes you will see that this also write in terms of primal variables and corresponding dual or surplus variable in each of these primal and dual, and then they will write in terms of that. Okay, now let us look at this. You can further interpret this as the complementary slackness condition says that for a positive basic variable in the primal, the corresponding dual variable will be equal to 0. Alternatively, if you take the non-basic variable in the primal Non-basic variables will be the slack variables or the surplus variable. Slack variable in case you have less than equal to type, and if you have greater than equal to type, it will be surplus variable, right? So what does it say? For a positive basic variable in the primal, the corresponding dual variable will be 0, and alternatively for non-basic variable in the primal, the corresponding dual variable will be 0. So we will look at this when we solve actual problem. We will try to see what it means, right? Okay, so let us look at how we can we have already seen how to write dual of a linear programming problem, but let us look at these things and see how we can possibly get the solution of dual from the primal when we solve using simplex method. Okay, so let us recall these user-defined functions that we have defined, namely pivot column, similarly pivot row, and then pivoting. These three functions I am just including here, and we will also write another program, user-defined function for finding all basic feasible solutions, because one of the results says that there is a bound for value of the objective function for any feasible solution. So we will write all the possible feasible solutions, and we will compare the value of the objective function for this. For that purpose, we have defined this. This is exactly same as what we have defined syntax for finding all basic feasible solutions, except that here I have created that as user-defined function. So we have returned what all the basic solutions, the list of basic feasible solutions. Okay, now let us look at a problem. So this is a linear programming problem, which is maximization type, right? And so if you convert this problem into standard form, this will be minimization of negative of this, all will be greater than equal to. So this is in the standard form that we are considering, right? But then in the Sage math, we'll think of maximization as standard problem, and whose dual it will write. So let us define this problem and convert this problem into a standard form. So we have defined the coefficient matrix A, the right hand side B, the cost coefficients C, and then write its dual in D, and then let us ask it to show the primal and the dual. So this is the primal and this is the dual. Again, you can compare the values, compare the design variables and the constraints in the primal and dual. In this case, all the design variables are non-negative. Therefore, all the constraints here are greater than equal to type. Here the maximization is original problem, which are all less than equal to, and this is the greater than equal to. So this is, there is no equality constraints. There is no variable which are unrestricted. So this is straightforward, right? Now let us look at what are the solutions of the primal and the dual. Okay. So if I look at the solutions of the primal problem has solution x1 is equal to 17 by 110, x2 is equal to 51 by 55, x3 is equal to 87 by 110, and the optimal value is 2434 divided by 55. Okay, this is the solution for primal problem. Now let us look at what is the solution for the dual problem using inbuilt Sage function. So you can see here the value of the optimal value of the primal and the optimal value of the dual, they are the same. Okay, that is what we have as one of the result. If one of the problem is optimal, the other one will also be optimal, and not only that, the optimal value will be the same. So that is what we are seeing here, right? Also try to compare. If you try to compare the values of the primal variables and the other slack and surplus variable in each of these problems, there will be relation. Okay, now let us ask it to show what is the P dot final dictionary. This is the final dictionary that this is inbuilt function in SAGE, but the final dictionary will give you the last actually, but for the surplus and slack variables, it will give you the final stage of the final simplex table, right? So if you look at this final table, final dictionary of this primal problem, what do you see here? The value is optimal because all the here the reduced cost coefficient are negative for maximization problem, therefore this is optimal, and this x1 value is 17 by 110, x2 value is 51 by 55, x3 value is 87 by 110, x4 has not entered into this, so x4 is 0 and x5 is 73 by 110, and optimal value is this, right? So in the original problem, if you look at the original problem, the design variables are x1, x2, x3, right? And they are all less than equal to constraints, so therefore the right hand side is going to be all slack variables. So the value of these slack variables in this case will be 0 here, right? So the value of the primal slack variables, x4 is 0 in this case because it does not enter, x5 is going to be 73 by 110, and x6 is 0, x7 is 0. Now if you compare this with this is your simplex, this is the dual problem. Look at the so if you look at this dual problem, this problem is minimization type greater than equal to sign, so one can solve this problem using big M method, because the standard linear programming standard simplex method will not work because these are greater than equal to type. So or you can use two-phase simplex method. However, SAGE already has the inbuilt function, so we will convert D to the standard form, and then we will again find out the final dictionary of this dual simplex method, right? Dual simplex problem. So if you look at this final simplex table, in this case again you will see that the value of the primal of the dual main variables y1, y2, y3, what are they? y1 is this, y2 is 0, y3 is this one, y4 is this, and optimal value is the same as the primal value, right? And the value of the dual surplus variables in this case, surplus variable because they are all greater than equal to, this is going to be y5 is equal to 0, y6 equal to 0, y7 is equal to 0. So now if you look at for example in this case, the x1 value is positive. The x1 will correspond to the first surplus variable in the dual. What is the first surplus variable in the dual? In this case that is going to be y1, y2, y3, y4, right? These are the 4 variables, so y5 it will be, so y5 value is 0 here, y5 value is 0, right? Similarly, if you look at, let us say in this case, let us look at, in case of primal, look at x5. x5 in this case, in case of primal, x5 is a slack variable, right? First slack variable is x4, second slack variable is x5. So second slack variable is x5, which is positive. Now the corresponding main variable in the dual, which will be y2. If you look at the y2 in the dual, y2 value is 0. So you see the relationship between the primal main variables of primal and the surplus or variables of the dual and vice versa, right? So that is the relation. This relation comes from the complementary slackness condition. Okay, so that is what is being demonstrated in this particular code. Next, let us look at so if you try to compare the solution of the primal dual pair, whatever we have observed, I am just putting it as a remark. So the slack variables in the primal corresponds to the dual basic variables in the optimal solution and the vice versa. Similarly, the value Cj minus Zj, that is the cost coefficient rows, under the columns of the slack or surplus variable. So if you look at the Cj minus Zj corresponding to slack or surplus variable, and ignore the positive sign, because for maximum primal objective function, the optimal occurs when you have all negative cost coefficient. So if you look at ignore this positive one, then what does it say? That directly it gives you the optimal values of the dual or primal basic physics function. So this, in the final simplex table, if you look at this the cost coefficient, look at the columns corresponding to the surplus variable or the slack variable, depending upon what problem you are dealing with, and look at the main variables of the dual one, then that there is a relationship. Okay, the optimal value of the objective function is same as the optimal value of the dual problem. That is what we saw, and primal slack variable times the dual main variable is equal to 0. That's exactly what we saw. If one is positive, the other one is 0. Right? Similarly, the primal main variable times the dual surplus variable is 0. That's exactly what we saw in this case. For example, y5 is 0, the corresponding x2 was positive, and so on. So these are the observations. So using these observations, once you have solved one problem using simplex method, the final simplex table will tell you the value of the solution of both primal as well as dual. That's what it means. Right. Let us explore the bounds on the primal dual pair. So let us consider this problem in three variables. Maximize 2x1 plus 3x2 plus 3x3 subject to these three constraints which are less than or equal to constraint, and then let us create this problem, write down its dual. So this is the primal, this is the dual, that is what we have. Now let us find out, so this, when you create P and D in standard form, it gives you all possible things, like it gives you the coefficient, it gives you the right hand side, it gives you the cost coefficient, it gives you the coefficient matrix A, and all the possible steps. We have already seen that. It also gives you what are the possible incoming variable, what are the ratio, all such things you get. Right. So here let us store the cost coefficient of the primal problem in the list C, and cost coefficient of the dual problem in D. So if you want, let us print what is C. The cost coefficients are 2, 3, and let us print what is D, that is 10, 60, 60, 10, 50, and that's what you have. The coefficient of the dual objective problem is 60, 10, and 50. So now let us look at, in case we find out all feasible solutions in case of primal problem. So this gives you all feasible solutions. So if you want, I can print what is Z values. Let me say print Z values. So this gives you, there are how many okay, no, this is not Z values. We'll have to say print S1. So when I say print S1, that is all the possible basic feasible solutions. These are the basic feasible solutions. 1, 2, 3, 4, 5, 6, 7, 8. There are 8 of them, and these are the value of the objective function at all these basic feasible solutions. Similarly, let us find out the value of the objective function for the dual problem. So there are 3 of them. There are only three basic feasible solutions for the dual. These are the value of the objective function at these value. Again, let us print S2, all possible solutions of the dual. So there are 3 of them, 1, 2, 3, and these are the value. Now if you look at any value of the primal, right, that is less than equal to the value of the dual. Okay, that's what you have. Now, if you contrast this with the problem that we have considered in this case, the primal dual, where is that relation? This z is bigger than equal to this. But then that says has the other way around. It considers the maximization problem as the original problem, right? The primal problem. Therefore, this relation will be other way around. That means W is going to be bigger than equal to Z, and that's exactly what you see here, right? If you compare the two values, any of this value will always be less than equal to any of this value here. That is how you compare the bounds, right? So these are the kind of relationship that you have between primal problem and dual problem. Not only that, if you are able to solve one of them, let us say primal or dual, whichever is easier, then the final stage will give you solution for the other one, right? If you solve the primal, then the last stage will also give you solution of the dual, and vice versa. If you solve the dual, if that is easier to solve, and look at the value of the final stage of that simplex table, that will give you solution of the dual problem, of the primal problem, right? So we will look at one example. We will do all the steps of simplex method of a dual problem. We will write dual of a linear programming problem. We will solve this using simplex method, and the last stage we will see that how we can get the value of the solution of the primal problem. Okay, so let me leave you with a few exercises. So the first three exercises are to find a dual of each of this problem. This is the first one, second one, and the third one. And the second problem, in the second problem, you write again the dual, and then find out all basic feasible solutions of the primal and dual, as we have done for one of the problem. Explore the relationship between the bounds, right? And then use the Sage inbuilt function interactive LP problem to find the optimal solution of the primal and the dual, and then explore the relationship between the primal dual variables, the main variable, or select variable, and surplus variable. So that is what you have to solve these things. Okay, so thank you very much. In the next class, we are going to look at a method to solve a linear programming problem, which is called dual simplex method. So remember, at present what we have is, if I have a linear programming problem, we can find its dual, and then we can try to solve dual using whichever applicable method is there. That is one way of solving. But then dual simplex method tells you that you don't need to actually write the dual, but then the same simplex method you can apply to the given primal problem. Of course, it will require certain condition, and then you can solve the problem. Okay, thank you very much.